Hello. So finally, now we have gone to the capsule 6B, which will be a roundup of the material for week 2. So the material for week 2 is rank and solubility, RNs, vector subspaces, linear spans, linear dependence, linear independence, basis, dimensions, row rank, column rank, and the equality of row and column ranks, and systems of linear equations. So we have defined vector subspaces of Rn. We have defined the notion of linear span. We have defined the notion of linear independence, linear dependence, and we have proved a very important lemma called the fundamental lemma, which enables us to prove that every vector subspace of Rn has a basis, and that any two bases have the same cardinality, and that's a dimension. We also use the fundamental lemma to prove that for a matrix, the row rank and the column rank are equal. We also did the determinantal rank, which is very important. And we finally saw the Kronecker-Capelli theorem, a necessary and sufficient condition for solubility of systems of homogeneous linear equations. So let us see what's there in these text slides. The rank of a matrix. Here, the rank of a matrix is defined as the number of pivots in its row echelon form. Now, this is quite different from the definition that we have seen. Let us now understand why this definition is exactly the same as the previous definition. Remember that how do I get a row echelon form from A? By performing a sequence of elementary row operations. Remember that when you perform a sequence of elementary row operations, neither the row rank changes nor the column rank changes. Because if a set of columns Ci1, Ci2, Cik are linearly independent in A, then after performing elementary row operations on A, the same set of columns Ci1, Ci2, Cik of A hat are again linearly independent. So the column space, so the two column spaces of A and A hat will have the same dimension, or the column rank will not change. The row rank obviously will not change because you're performing row operations on a set of rows. So it is enough. So the rank of A is the same as the rank of the row rank of A is the same as the row rank of A hat. The column rank of A is the same as the column rank of A hat. So what is the row rank of A hat? It is basically, so how many pivots are there? The pivot, there is a pivot in the first row, there's a pivot in the second row, there's a pivot in the third row, etc. And there's a pivot in the kth row. After that, everything is zero. Similarly, you look at the pivots, the columns containing the pivotal columns. Now the pivotal columns are linearly independent, remember? In A hat. And so the very same columns in A would be linearly independent. And that should convince you that this definition of rank as the number of pivots, because the number of pivots is the same as the number of pivotal columns, and the pivotal columns are the linearly independent ones. Every other column is a linear combination of the pivotal columns. And so that basically should convince you that this definition of rank and the earlier definition of rank are one and the same. So then comes the solvability of systems of linear equations. A system of linear equations is solvable if and only if the rank of the associated matrix equals the rank of the augmented matrix. Now, if the nullity is zero, then and the system has a solution, that solution will be unique. The system, if the system has a solution and the nullity is positive, then there will be infinitely many solutions. Because remember, how do you obtain all the solutions? You take a specific solution and add all the elements in the null space, and you get your solution set. So when will the nullity be positive? The nullity is positive means the rank has to be less than n. Rank plus nullity is the number of columns, n. And so these are being summarized as theorem 2 in this slide. And we already done the proofs, and I shall not go through the proofs again. And null space. What is the null space of a matrix? It is a set of all vectors x such that ax equal to 0. And the dimension of the null space is called the nullity of the matrix. And the last line in this slide, the slide says that if you have a particular solution of the inhomogeneous equation ax equal to b, then the general solution, the complete set of solutions is simply add to x naught all the elements in the null space and you form your solution set. So let us now look at an example. Here is a system of inhomogeneous system of linear equations. You got three equations in five unknowns. Three equations in five unknowns. It's inhomogeneous. There's a right hand side 2 to alpha, and the augmented matrix is displayed on the slide here. And now we want to understand whether this system has a solution or not. The first column is identically 0. There are no pivots in the first column. No matter what row operation you perform, you're not going to make that non-zero entry, and you're not going to get a non-zero entry in the first column. The first column remains 0. So there cannot be any pivots in the first column. Okay, now after performing row operations, the row echelon form, not row reduced, excuse me, row echelon form is displayed here. So what is the rank of the associated matrix that is the left of this vertical line? The first 5 columns only you take. That's the associated matrix. The rank of the associated matrix is evidently 2. What is the rank of the augmented matrix? The rank of the augmented matrix will become 3 if 16 minus 2 alpha is not equal to 0. That is, if alpha is not equal to 8, then the rank of the augmented matrix will be 3. So the system will not have a solution. Whereas if alpha is 8, then the rank of the associated matrix, as you can see, is the same as the rank of the augmented matrix, right? The second column and the third column are linearly independent, and this last column is a linear combination of the second column and the third column. So the column rank doesn't change, and hence the rank doesn't change. Row rank equals column rank, so not a problem. Now, which are the free variables? Which are the pivotal columns? Column 2 and column 3. Which are the non-pivotal columns? Column 1, column 4, column 5. So which are the free variables? x1, x4, and x5. Which are the non-pivotal one? Which are the other variables? x2 and x3. So x2 and x3 have been expressed in terms of x1, x4, and x5. x1, x4, and x5 are free variables. They can be assigned arbitrary values. Whatever values you wish to assign them, you can do so. So what value shall we assign x1, x4, and x5? Obvious choices. I will take x1 equal to 1, x4 equal to 0, and x5 equal to 0. And then what I could do is that I could just momentarily solve the homogeneous equations. So instead of 8, 2, and 0, I can just forget the last column. And so these constants 1 and 5 will disappear. And you simply take x1 equal to 1, x4 equal to 0, x5 equal to 0, and then you find your remaining two variables x2 and x3. That will give you one solution of the homogeneous equation with 0 right hand side. That will give you one element in the null space. Another option is to take x1 is 0, x5 is 0, and x4 is 1. Again, take 0 in the augmented column. You will get another solution of ax equal to 0. That will get one more element in the null space. Take x1 0, x4 0, and take x5 equal to 1. Again, make the right hand side 0, solve the equation, and you will get the third element in the null space. These three elements will be the basis for the null space. Okay. So there's one more example of a similar kind with A's and B's. Yeah, by the way, going back to the previous example, the complete solution is what? x1, x2, x3, x4, x5. Suppose if I take x1 equal to 0, x4 equal to 0, and x5 equal to 0. If all three are 0, then what is the solution? x1 is 0, x2 becomes 5, right? x3 becomes 1, x4 is 0, and x5 is 0. So you get 0, 5, 1, 0, 0. That's a particular solution. You found a basis for the null space, correct? You found a basis for the null space. Let's call them n1, n2, n3. And you found a particular solution. What is that particular solution? 0, 5, 1, 0, 0. So that's your x0. That's your particular solution x0. So add to x0 all the elements in the null space. You know three vectors in the null space which are the basis of the null space already. n1, n2, n3. So you should take an1 plus bn2 plus cn3, where a, b, c are arbitrary real numbers, and you'll get all the elements in null space. And you have to add these things to the particular solution, namely 0, 5, 1, 0, 0. And you'll get the complete solution set. Okay. In fact, on a Wednesday tutorial class, one example is going to be done in detail. We already done one such example in the very first lecture. We have done one complete example. We have written down the solution in the form of a constant vector plus a times a vector plus b times a vector plus c times a vector, where a, b, c are arbitrary real numbers. They are the free variables. So that is done. And here is one more example of a similar kind. Dimension. Here is some motivation for dimension. Again, some planes, etc. are being planes and lines in R3 are being looked at, and so the solutions is a solution is it's a plane, and so and the second one, the first example is a plane, and the second example is a line, and the examples are being motivated. The definition of a basis is being motivated with the example. We have already done a similar example. So vector subspace. What is the vector subspace of Rn? A vector subspace of Rn is a non-empty set V, such that whenever I pick two elements in V, and then the sum should be in V. And if I take an arbitrary scalar A times V should also be in V. These two can be combined in one sentence. If you take two arbitrary vectors V and W and two arbitrary scalars A and B, and then AV plus BW should be in V. This is completely equivalent to what we have done. It's just a minor, it's a formatting, it's formatted differently, that's all. And then there are examples of linear span, there are examples of vector subspaces and linear span. You are given a set of vectors in Rn, and you take all possible linear combinations of these vectors, and you get the linear span. And the linear span, or you also say that L of the vector space, LS is the vector subspace generated by V1, V2, Vk. That's another way of saying it. So now let us take this example. We have taken V1, V2, V3, three vectors in R2, and we take the linear span of V1, V2, V3. But it turns out that the third vector is a linear combination of the first two vectors already. So the linear span of V1, V2, V3 is going to be equal to the linear span of V1 and V2. So throwing in the third vector is redundant. So the linear span of V1, V2, V3 is the same as the linear span of V1, V2. Or the second vector V2 can be written as a linear combination of the first and the third. So if you want, you can drop the second vector and keep the first and the third. Or you could keep, or the first vector V1 is a linear combination of the second and the third vector. Or if you like, you could drop V1 and you can take linear span of V2 and V3. So no matter how you do this, you're going to get the whole of R2. So there is a certain amount of redundancy. So taking this redundancy can be, so what we do is that this idea of taking the spanning set or a set of generating vectors and dropping redundant vectors systematically, ultimately you will land up with a basis. You can't drop two of them. If you drop two of them, you're not going to get the whole of R2, you're going to get a line. So maximum you can drop one of the vectors. Then we have the definition of linear dependence. A set of vectors is said to be linearly dependent if there is at least one, if there is a set of, there are scalars C1, C2, Ck, at least one of them which is non-zero, such as C1, V1 plus C2, V2 plus Ck, Vk is 0. The opposite of linear dependence is linear independence. So negation of linear dependence is linear independence. So how do you negate it? A set V1, V2, Vk is said to be linearly independent if whenever C1, V1 plus C2, V2 plus Ck, Vk is 0 as displayed here, C1, C2, Ck must be compulsorily 0. This is equivalent of saying that no Vj can be expressed as a linear combination of the others. So you try to do this with three vectors. What does it mean for three vectors? And you will get the general idea. Now, the notion of linear independence and linear dependence is very fundamental, and it doesn't. When you stare at this definition, the fact that the V's are columns or the V's of rows, the specific nature of the vectors don't come into play. The size of the vectors, etc., don't come into play. So this definition of linear dependence, linear independence, linear span, they are susceptible to generalizations. And when you generalize this, you get the theory of abstract vector spaces, abstract linear algebra. That you shall see later in further courses that you will take in subsequent semesters. And basis and dimension. What are the basis? A subset. So first of all, you take a vector space V sitting inside Rn. A subset B is called a basis if it is linearly independent and it generates V. The linear span of B is V. Okay. Now what happens if I take the vector space to be a zero vector space? If I just take V to be consisting of zero vector alone, then remember that the empty set is linearly independent and the linear span of the empty set is an empty sum. Empty sum is conventionally given the value 0. And so the empty set is the basis for the vector subspace consisting of the zero vector alone. Now we have seen using the fundamental lemma that every vector subspace of Rn has a basis and any two bases have the same cardinality, and this number is called the dimension of the vector space. And so now when you take a M cross N matrix, you take a matrix with M rows and N columns. The rows of the matrix, they can be regarded as vectors in Rn. And the linear span is called the row space of the matrix. The columns of the matrix can be thought of as vectors in Rm. And their linear span is called the column space. The dimension of the row space is called the row rank of A. The dimension of the column space is called the column rank of A. And the fundamental result is that the row rank of A is the same as the column rank of A. This common value is called the rank of A. And if I perform an elementary row operation on a matrix, the rank does not change because the row rank doesn't change trivially. So these are proofs of these theorems. We already discussed these proofs, and I will just equality of row rank and column rank I already discussed. And there are some more examples on row echelon forms and extracting linearly independent subsets. So here you got a bunch of vectors v1, v2, vk. Okay. Now I want to, if this set is linearly independent, do nothing. If it is linearly dependent, then one of the vectors is a linear combination of the others. And so this particular vector, which is a linear combination of others, can be dropped and you get a smaller set. If the smaller set is linearly independent, stop. Otherwise, delete one more vector, which happens to be the linear combination of the others. By this process, infinitely many steps, you are going to get a subset of this highlighted set, which is linearly independent, and the linear span of the subset is the same as the linear span of this whole thing. And so this set will contain a basis. So if you look at the vector subspace generated by v1, v2, vk, then this generating set will contain a basis. This is what it means, that you can delete a bunch of vectors from this set and retain a linearly independent subset, and you'll get you'll get a basis for it. How to do that has been illustrated with a simple example. And the rank nullity theorem. If you take an M cross N matrix, then the rank of A plus the nullity of A is a number of columns of A. So this is called the rank nullity theorem. And a proof of the rank nullity theorem has been given. This proof is essentially, the proof that is given here is essentially the proof that we have given, except that the way it has been presented, the formatting is slightly different. Formatting of the proof is slightly different. And so with this, I think I will close this. And here is one more example using the row echelon form. So, Okay, so now here there is an example in the rank nullity equation. So you are taken a 1, 2, 3, 4, a 4 by 5 matrix. A sequence of elementary row operations are being performed. A sequence of elementary row operations are being performed, and it ultimately gives you the row echelon form. So where is the first pivot? The yellow square 1. The second column is the multiple of the first column. So the second one is a non-pivotal column. The third column is linearly independent of the first two. So the next pivot appears here. So the third column 3 is a pivotal column. The fourth and the fifth columns are obviously linear combinations of the first and the third. And so these are also non-pivotal columns. So what is the rank of the matrix? It's 2. What is the nullity of the matrix? 3. How many free variables are there? 3. Which are they? x2, x4 and x5. Push x2, x4 and x5 to the right hand side and solve, you get the null space. And so if I assign x2 the value 1, x4, x5 0, 0, you'll get one element. Then after that, take x4 to be 1 and x2 and x5 to be 0, you get another one. You get x, and then finally you take x2 and x4 to be 0 and take x5 to be 1, you get a third one. These three vectors will form a basis for the null space. That's exactly what is being done. x2, x4 and x5 can take any values, and so let us assign them values 1, 0, 0, 0, 1, 0, 0, 0, 1, and the corresponding solutions are written down, v1, v2, v3. They give you the basis for the null space. So what I said earlier has been now illustrated with a nice example, numerical example. So I think with this, I will stop this lecture 3. I'll stop lecture 3 with this. Thank you.